So let's go ahead and look at the mechanism of the synthesis of aspirin. So first of all, we have an acid, and the acid that we use is sulfuric acid. I'm just going to label this HA. And then we also have our acid anhydride, specifically acetic anhydride. And finally, we have our salicylic acid. I'll put this in blue. So this is an aromatic ring or a benzene ring. And it has an alcohol. And coming off the carbon right next to that, there is a carboxylic acid. Okay, so these are the three things that we have to think about. So in the first step, what we have here is activation of the carbonyl group. Okay, so we have our acetic anhydride. And what we notice about this anhydride is that it is symmetrical. And so that's important because when this reaction is happening, the alcohol that is on the salicylic acid can actually react with either this carbon right here or this carbon right here. And depending on which carbon it reacts with, then this little group right here, along with this, will be attached to the salicylic acid. But since this is the same as this, it doesn't really matter which side of this anhydride the alcohol reacts with. It will be the same product either way. So the first thing that happens is the acid is going to act as a catalyst in this reaction. And if I put my acid over here, what happens is this lone pair is going to come over here. It doesn't matter which lone pair it is or which oxygen. I just randomly chose the left oxygen on the left carbonyl group. Is going to go ahead and form a bond with the hydrogen. Now the bond here is going to jump on as a lone pair for the acid. And so what we will get is this structure right here. And this oxygen has a positive charge on it. And we have this conjugate base that's left over here. Now what I'm going to do here is I'm going to show you through resonance why adding a proton to the oxygen on the carbonyl group right here is going to activate this carbon right here. So a second structure could be shown like this. If this pi bond is to jump onto that oxygen right here, then what we will be left with will be this structure. Still have that proton that's connected to the oxygen. However, now this carbon only has 3 bonds. and therefore it has a full positive charge. So this is where the salicylic acid is going to come in. So we have our carboxylic acid group right there, and we have our alcohol right here. So the alcohol is a nucleophile. We have our electron dense area. It's going to come in and it's going to form a bond with that carbocation right there in that resonance structure. Now, what we're going to be left with will be this molecule here. Got our proton. And now the positive charge is on that oxygen. So now our conjugate base is going to be right here. And the conjugate base is going to go ahead and deprotonate this oxygen, take that proton off there, and that bond is going to jump onto the oxygen. And then what we will be left with Hey, pretty good. How about you?
Pretty good.
And just like that, our acid has been reformed. So our acid now has that proton on there, hence the catalyst. Okay, so in this step, what's going to happen is we're going to start to reform our carbonyl group. And these oxygen right here, the lone pair is going to go down and reform a pi bond. Now what happens is this carbon that's right here can't have 5 bonds. So one of the bonds is going to break. Now what's going to happen is that this bond for between this oxygen right here and this carbon right here is going to just jump on as a lone pair onto this oxygen. And the reason why, I'll show you in just a second, is because this is going to be a good leaving group. So this right here is something we're going to call a leaving group. So leaving group is an atom or group of atoms that breaks off the main molecule during a chemical reaction. Okay, now why is that a good leaving group? Well, what we're going to form is actually acetate. So here we have a double bond. This oxygen now has proton. Actually, somewhere along the way, that actually should be the original proton that came off the acid there. Just keep our color coding correct. And now we have this. So kind of shifted the way the molecule was angled. And that's just to kind of keep our sp3 angles in the correct order. Okay, and we have this along with this right here, our acetate. And this has a negative charge on it. But the reason why that's stable is because what we can do is have resonance that actually distributes this negative charge. So one of these three lone pairs will come down here, it will make a double bond, but then this double bond is going to jump up as a lone pair. And so now we have the second structure where this oxygen has that negative charge. Okay, we are almost complete with our aspirin molecule. Only thing is, this is going to kind of be a reach around, but this negative oxygen is going to come over here and it's going to grab the hydrogen, and then that bond is going to jump onto the oxygen. And so what we're going to get is going to be acetate. Sorry, not acetate, acetic acid, plus our aspirin. And okay, So with that being said, this group right here is what we refer to as an ester. This is just a side note. So that right there is going to be an ester. And then we have this right here, which is our carboxylic acid. So two different functional groups are on this benzene ring or this aromatic ring, and together, or all three of them, right here, come to create the aspirin. So again, let's go ahead and just do a quick overview from the very beginning. We have an acid that's going to act as our catalyst. In this case, we have an acid anhydride, specifically acetic anhydride, because we have one carbon here and one carbon here. So acetic is going to be the common name for two carbons. And we name our acid anhydrides by the groups that are on each side of this oxygen right here. So there we got that. Right here is our salicylic acid. Salicylic acid has a carboxylic acid on it, and it has an alcohol that is missing one electron right here and one there. I don't know what happened to those. Okay, so the first thing that happens is activation of the carbonyl group, and so that's when one of these two oxygens right here that's double bonded to the carbon. In this case, it doesn't matter which one because we have just a carbon right here and a carbon right here on both sides, and so it's symmetrical, is going to grab onto the hydrogen, and then we're going to be left over with this conjugate base over here. Now, it doesn't make sense at first why this so-called activation occurs, but if we think about the resonance structure, the resonance structure is going to, here we go, show us that if the double bond here, the pi bond, moves up onto the oxygen, that we're left with a carbocation, and this is going to be very, very attractive to a nucleophile, specifically the alcohol group on the salicylic acid. So the oxygen is going to go ahead and come in here, and it's going to form a bond with this carbocation, and we're going to be left with, let's see, this intermediate structure right here. And so our conjugate base is then going to go ahead and it's going to come over here and it's going to take this proton off of that oxygen, and then that positive charge is no longer going to be there. And we're going to be left with this structure right here. Now, what we want to note is that this lone pair is going to come back down and form a double bond. But when that happens, one of these bonds has to break. Now, it turns out this bond right here is going to break because when it does break, the leaving group is a very stable structure that we call acetate. And it's stable because what you're left with is a structure that can distribute the negative charge into both of these oxygens. And that distribution of negative charge leaves a very stable structure. Now, we also have a positive charge right here, which I did not note. But what's going to happen is that our acetate ion is going to go ahead and grab the hydrogen off of this positively charged oxygen right here. And the bond that was between the oxygen and the hydrogen is going to jump onto that oxygen as a lone pair. And that is going to leave us with our final products, the acetic acid and the aspirin.